Hello, I'm Dr. Derek Keats, a former professor of biology, and I'm continuing with you on the topic of homeostasis. In this video, we're going to look at the role played by negative feedback in regulating the body's water levels and salt concentrations. Now remember that homeostasis is about maintaining constant and optimal internal conditions. Now the regulation of water in our bodies, also called osmoregulation, is vitally important since water makes up around 60% of our bodies by mass. It varies with age, being much higher in babies and much lower as we get older. Now, if the water level is much higher in our bodies or much lower in our bodies than this, then we have big trouble. So now let's look at how this water balance is maintained. Now, in order to do that, we need to review a little bit about the kidneys from what we learned in grade 11 under the topic of excretion. Now remember, the kidney is a three-dimensional structure. And when we look at images like this, we are looking at a stylized drawing through a very thin slice of a kidney. And a typical kidney can be seen to have three obvious layers. The renal pelvis that collects the output of the kidney and sends it to the ureter, from where it moves into the bladder for storage. A medulla, meaning middle, which is divided into rounded pyramid-shaped regions, and an outer cortex. Now, you can also see the renal artery, which brings in oxygenated blood, including the blood that is going to be cleansed by the kidney, and the renal vein, which takes away the deoxygenated and cleansed blood. Now, each kidney also connects to the ureter, as noted, and this takes away waste to be stored in the bladder. Now we're going to introduce the most important structure of the kidney, the nephron. And remember these pyramids, the pyramid-shaped structures in the medulla. And you can see that there's sort of a pyramid shape that passes from the pelvis through the medulla, and you can see it more or less in the cortex as well. And it's within these extended pyramids that you find the nephrons. Now, a typical human kidney contains around 1.5 million nephrons, so you can imagine that this one shown here is not drawn to the correct scale. So the nephron is the basic functional and structural unit of the kidney. And as you can see, the nephron extends from the cortex through the medulla, with a little bit of it sitting within the pelvis. Now, the nephron is responsible for four key processes, and these are interrelated processes that happen in the kidney: filtration, secretion, reabsorption, and excretion. Now let's take a superficial overview of what happens in the nephron, purely as review, so we can understand how water is regulated. Now the front end of the nephron is the Bowman's capsule, which in 3 dimensions is rather like a tennis ball. And you need to imagine this as a tennis ball, not as this sort of C-shaped structure that you see here. So it's rather like a tennis ball with a hole in one end, and it's connected to a tube at the other end. Now, entering through the hole at one end is a blood vessel. Well, there are 2 blood vessels. There's an incoming blood vessel and an outgoing blood vessel. And these blood vessels branch and anastomose into a capillary bed called the glomerulus. Now, here's a diagrammatic representation of the Bowman's capsule and the glomerulus. And you can imagine blood entering one end of this blood vessel, wending its way through the capillary bed, and eventually out into the renal vein. And as this happens, a filtrate is produced as the liquid from the blood passes out into the Bowman's capsule from the glomerulus. And then the filtrate is taken away, and various things happen to it along the way. The reason the liquid from the blood is forced out is due to blood pressure. So let's look at the nephron and look at the filtrate and how it passes through the proximal convoluted tubule, which in reality is surrounded also by blood vessels. There's some excretion here and also some reabsorption of some of the components that are now in this tube. The filtrate passes through the loop of Henle, where reabsorption continues, and as the filtrate passes through the distal convoluted tubule and the collecting duct, various things happen. There is reabsorption of some of the things that are forced out into the Bowman's capsule earlier on. From the collecting duct, the filtrate passes into the ureter, from where it moves into the bladder as the substance we call urine. These collecting ducts are also connected to other nephrons, because this is a whole three-dimensional interconnected structure. So here we can imagine the filtrate being collected and passing into the bladder. Now we've reviewed this because we want to talk about homeostasis and the maintenance of the water levels of the blood. Now let's imagine that the water level of the blood rises. This might happen because of cool weather, we're not sweating very much, or because we drink a lot of fluids, or maybe because we're sitting around using the computer or watching TV. Now when this happens, the detector, the equivalent of the thermostat in our air conditioner example, are osmoreceptors in the hypothalamus, and these signal the pituitary gland. And ADH, antidiuretic hormone or vasopressin secretion, is decreased. When this decrease in vasopressin secretion happens, the permeability of the nephron ducts, remember those ducts, those tubes that run out of the Bowman's capsule. The permeability of these tubes is decreased. And when this happens, less water is absorbed, and so we get more dilute urine, because less water is reabsorbed back into the blood. There is more water in the filtrate that is now passed into the collecting duct and then onto the bladder. And so we have dilute urine. And as a result of this, more water is lost, and the water level in the blood returns to normal. But what happens if the water level in the blood falls? For example, there's hot weather, we're sweating a lot, or we don't drink very much fluid, or we're exercising a lot. Then the osmoreceptors, our thermostat for water, maybe we should call it a water stat. Osmoreceptors in the hypothalamus signal the pituitary gland again, and ADH secretion, that is antidiuretic hormone or vasopressin, is increased. So the secretion of ADH is increased. What this does is it causes the permeability of the nephron ducts to be increased. Now with the increased permeability, more water is reabsorbed, and therefore less water is lost and taken out in the collecting ducts and carried down to the ureter and then onto the bladder. So we have a more concentrated urine, and because less water is lost, we're able to restore the normal water level in the blood. Now all of this happens due to the way in which negative feedback through the secretion of hormones influences how the nephron interacts with the surrounding tissues and blood vessels. And so we see this little structure, the nephron, is very important to our bodies and to the maintenance of water levels of the blood and osmosis. Now salt balance also follows a negative feedback loop, and we've seen this before when we were studying the endocrine system, so we're just going to review it a little bit here. So we're going to start with normal sodium concentration in the blood, and imagine what happens if sodium ion concentration in the blood decreases, that is, it gets lower. Well, aldosterone secretion is increased, and aldosterone has an influence on both sodium ion excretion and sodium ion resorption. So we get an increase in sodium ion resorption, that is, more sodium ions are taken up out of the fluid that is now in the, where? In the nephron, in the tubules of the nephron. Now, there's also a decrease in the excretion of sodium ions as the filtrate passes through the nephron. So therefore, the sodium ion concentration of the blood increases, and following this decrease, then through this process, normal sodium ion concentration in the blood is restored. What happens if sodium ion concentration increases? That is, it gets higher. There are more sodium ions in the blood, and this is bad for us. Well, aldosterone secretion decreases, and this leads to a decrease in the sodium ion resorption and an increase in the sodium ion excretion, and so more sodium ions are lost and the normal sodium concentration of the blood is restored. And our detector mechanism here and the way in which this happens is through adrenocorticotropic hormone ACTH, and we've seen this already previously. And so here we have another negative feedback loop that is involved in homeostasis. Now, we've pretty much covered what you need to know for the South African Grade 12 Life Science syllabus on the subject of water and salt balance. If you want to take it further, maybe you could Google for things like kidney, urinary system, nephron, osmoregulation, salt balance, etc. Any of the terms that we've used. You could look for videos on YouTube. You could visit the local library and read up on this topic. And if you do find something good, please remember to post the videos in the wiki or post links to any good content that you found in the wiki. And that's all for now. I'm Derek Keats, and this resource is licensed under a Creative Commons Attribution license.